Okay, we are back here talking more about chemical compounds and chemical equations. All right. So, um, so in chemistry, we sometimes have a situation where two compounds have the same formula or the same number of atoms and same number of atoms and kinds of atoms. So we say something, two structures have the same chemical formula. Uh, they they will have the same number of atoms and the same types of atoms. But you see here, they have the same chemical formula. So this chemical formula right here is C2H6O. Whereas this one is also C2H6O. So you see they have the same chemical formulas, but different structural formulas. So different structures. So they'll have the same chemical formulas, but different structural formulas. And you see in this example right down here, they have also the same chemical formula, but different structures. See, one is very open chained here. So one is very open chained here. This one is very open chained, or it doesn't have any cyclic character, whereas this one looks really different, and this one here has a cyclic structure. So very different structures. So here we could say very different structures. Very different structures, but same chemical formula. Okay, so formulas give us insight into like what type of atoms are present, but they don't tell us anything about what actually the structure looks like. And these lines here, remember they in chemistry they're not physical lines, so they're not used to represent anything kind of concrete or that has some physical existence. These lines are to represent chemical bonds or forces. And we know forces, they have no really physical manifestation. They're kind of invisible to us. They're but we can feel forces like the force of a magnet, right? You can feel the force of repulsion. That's like what these forces are, but it's a force of attraction. And to kind of illustrate that force, we use lines to denote chemical bonds or forces between two nuclei. So just to maybe clear that kind of concept, make sure that's understandable. All right. So both these structures have the chemical formula. Let's count it up. So I didn't draw it here, but there should be a carbon atom here. So let's put a carbon atom here. That's a different notation. If you go to OChem, you will understand why sometimes we leave the carbon atom out and don't write the C, and why sometimes we keep it in there, keep it represented like I did here. All right, so we have 3 carbon atoms, so we're gonna have C3, and if we go to both structures, we see 3 carbon atoms for both. And then hydrogen is going to be H6 for both cases. And in this case, we have 1 oxygen atom in both structures. So C3H6O. So be able to maybe draw a structure. Well, I won't say draw, but write a chemical formula based on the chemical structure. And then eventually we'll be able to write structures where we're given the chemical formula and write the best structure for the chemical formula. Now, this chemical form, if we give an example like this, it's kind of hard to say, oh, which one is correct, because But we'll go more into that when we talk about Lewis structures. But just keep in mind that we'll have to be able to draw these structures when given a chemical formula. Okay, that's an important skill when learning chemistry. Okay, so these structures we refer them as what we call isomers. So if two structures have the same chemical formula, but they are not the same compound or the same structural formula, they have different physical and chemical properties, and we call those isomers. So iso means kind of like different. Isomer, it's basically the same formula but different structure. So we can't call them the same thing because they're different. So we call them iso or isomers. All right. So in our chemical compounds, we have binary compounds. So binary compounds are compounds that are formed between two elements. Okay. Some examples are water, hydrogen, and oxygen. So we have hydrogen and oxygen. Okay. And then we have some other examples like sodium chloride, and here's another example, magnesium chloride, or magnesium, let's say magnesium iodide. Okay. Another thing we should know is that we have to know the elements by their name and chemical symbol. So if you're not, if students haven't memorized most of the chemical elements and their symbols, now it's we're going to be working through a lot of these problems. So it's important that given every problem, you can identify the element by name and by its chemical symbol. So a common mistake is people will call magnesium manganese, but that's wrong. So magnesium, Mg is magnesium, manganese is Mn. So even though magnesium does have an N in there, I see where it can get confusing. But manganese also has a G, right? So it can be confusing. So try to differentiate those two. So magnesium, Mg, manganese, Mn. Okay. Okay. But let me just double check here because sometimes, when I say things a lot, I tend to then mess it up. So let's just double check here. Yeah, manganese. So yeah, kind of confusing, manganese and Mg. So just kind of get those two squared away, and know that magnesium is Mg, manganese Mn. All right, magnesium and iodine here, or iodine, however you want to say it. And another example for binary covalent compound is something like SO2. Sulfur and oxygen. So those are what we call binary compounds, and they're the most prevalent in terms of many of the base like small compounds that only have many of the compounds that we see are mainly binary. Sometimes they're ternary, which means a compound made of 3 different elements, but those are much more rare. And fewer examples there, but most of them are binary. So hydrogen chloride, sodium chloride, barium chloride, etc. But they're usually we don't talk much about like ternary. It's usually more binary compounds. So that's probably the most common one we'll see. All right, polyatomic ions. So polyatomic ions are basically ions that have a charge, but they're made up of more than one atom. So the charge of the ion is the charge of the whole structure, not just the individual atoms. The atoms all have some charge, and they all add up to +1, +2, whatever the charge may be. So polyatomic ions that are formed from two or more atoms that are connected with covalent bonds. Okay, so those are polyatomic ions. So some examples are, some examples are the ammonium ion, so NH4 plus. Okay, so this plus just means the charge overall on the structure is plus. It does not mean hydrogen has the positive charge, so that's not what that means. So this is what we call ammonium ion. So this is the ammonium ion. So that's ammonium ion, and then we have OH minus. This is called hydroxide. Ion. Then we have some more complicated ones. CO3, 2 minus, carbonate ion. This is the carbonate ion. So when we name ions, we just name the name of the structure and then the word ion at the end. So carbonate ion right there. And then we have, this is one last one, phosphates. So PO4, 3 minus. So when we have polyatomic ions, we just have to kind of memorize the charges. There's no good way to remember them, or the way to remember is pretty much memorization, or if you learned previously, we usually considered the acid or base form of the molecule, and compared to that, to form the ion, we would either remove a hydrogen atom, and that would cause a negative charge to appear for that ion. So in the case of carbonate, there's 2 hydrogens from carbonic acid. So each hydrogen we lose, we get a negative charge in the ion, or the conjugate base, or the ion that's left after the hydrogen atoms are removed. So carbonate will be CO3 2 minus, because carbonic acid is H2CO3. And phosphate comes from phosphoric acid, which is H3PO4, the neutral compound. So we remove 3 hydrogens. That means to conserve the charge balance, phosphate will be turned into 3 minus, so phosphate ion. Okay, so that is some polyatomic ions. Let's move on now to molecular and empirical formulas. So in discussion, we will do a lot of examples where we determine molecular and empirical formula, but that will be in a later chapter. Just giving you a heads up what to expect. So what is the difference between these formulas? We have different formulas, right? There's chemical formula, molecular formula, empirical formula. So chemical formula is basically just the chemical makeup of the compound itself. So it's pretty much an abbreviated form of the structural formula where you just list the total number of atoms and the kinds of atoms, what atoms there are. All right, so our molecular formula, we have, it's basically a chemical formula. So a chemical formula that describes the actual makeup of the compound. So when we say chemical formulas, there's two ways we could represent it. We could represent it as the actual number of atoms in the compound, or we can abbreviate it. So chemical formula just tells you the type of atoms and the number of atoms present. It doesn't tell you if it's the actual number or a reduced fraction or a reduced ratio of let's say carbon to hydrogen atoms. So it could be a reduced ratio or like a simplest terms kind of ratio, like in math, or it can actually tell you the exact number of each atom compared to the other atoms in the structure. So there's two types of chemical formulas there: molecular formula and empirical. So molecular is the actual makeup, empirical is the reduced form. Okay. So sometimes the molecular formula can be the same as the empirical formula. Okay. So for example, let's say we have C6H12O6. So this is a formula for glucose, but so the most common formula of the most common compound you associate with this formula is glucose, which is the carbohydrate our body recognizes or uses as the main source of energy for the cell. So we convert glucose into carbon dioxide, water, and oxygen. So we use that to and that in turn causes energy to be produced and consumed by the cell or our bodies. Okay, so that's how our primary source of energy. So that would be an example here, glucose. Oh, but don't worry, you don't need to know this name by heart. But I'll use examples where I write this structure, and I'll be referring to it'll always be referred to as glucose. Usually in all of the examples I will show. Okay. So empirical formulas. What are empirical formulas? Okay. So empirical formula is the simplest So it's the simplest whole number ratio of elements in a compound. For example, our glucose example we just drew or wrote above, H12O6. So we can reduce this to simplest terms by taking out the factor 6, right? So this would equal 6, and we would get a ratio of C1, H2, O. Right? So we could write that. So our empirical formula would be CH2O. So this is the empirical formula. Is the empirical all right. So another example is C4H8. In this case, we can take out, we could factor out the 4, and our formula now turn into CH, and 4 times 2 gives us 8. So CH2 is our empirical formula. So CH2. So CH2 has no real chemical meaning, because if you try to draw a structure for CH2, you notice that carbon is missing 2 atoms. So carbon would look weird with just a CH2 group. So you know that can't be the molecular formula, because there's too few atoms for carbon to have an octet, or 4 atoms around it. So in the sense of chemical bonding, this wouldn't make sense chemically, but in essence, it's used to refer to like what percentage of the compound is carbon and hydrogen. And if you were to compare the empirical formula with the molecular formula, that percentage is the same. So that's what empirical formulas are meant to be. Is it's supposed to reflect just what percent, relatively speaking, what percent of the compound is made up of carbon, or made up of magnesium, of chlorine, whatever the atoms are in the compound. So CH2 would be the empirical formula. Okay, so let's end this video here, and we'll pick up on in the next video, where we'll talk about now nomenclature. So remember nomenclature. We want to remember how to name things, because that you could probably see that on the first exam. Okay, so nomenclature is next. See you then. See you in the next video.